Broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and thank you for being here with us. Thank you for attending Tuesdays with SOLIDWORKS. As you may know, we are conducting this session every Tuesday, and we have been here since April. Imagine that. We are conducting a technical session each and every Tuesday. The main goal from this session is stay connected with you, listen from you. So please, we are expecting a lot of interaction from your side. If you do have any challenge seeing the screen or maybe hearing my voice, please let me know. Just push me anything in the chat area or through the question area. Last Tuesday, we have been speaking about SOLIDWORKS Manage. We have been going through all real scenarios related to SOLIDWORKS Manage. Today, it's a very specific topic related to SOLIDWORKS Motion. We will go through a deep technical details in SOLIDWORKS Motion. And today with us, we have a very special guest coming from CAD/CAM SIEM. CAD/CAM SIEM is the engineering solution provider. They are located mainly in Egypt, but they are providing different solutions in over the Middle East. So today here with us, Mahmoud Alkaluby. He's a senior application engineer, SOLIDWORKS expert, and of course, professional in SOLIDWORKS Motion. I will not take a lot of time from you. Let's the show begin. So, Mahmoud, the stage is yours. Can you unmute yourself, please?
Yes. Hello, everyone.
Yes. Now we can hear you. Go ahead, please, Mahmoud.
Okay. Hello, everyone. Today we are going to discuss about SOLIDWORKS simulation tools. So starting with SOLIDWORKS simulation tools, SOLIDWORKS come in 3 different packages for structured tests. These packages are simulation standard, simulation professional, simulation premium. Also, we have flow simulation, and that's product for simulating the liquids, gases, and heating and cooling. Also, we have a special product for mold called plastic, which can check mold effects and make sure you have good plastic part. We have also SimulaWorks, and SimulaWorks is based on Abacus Solver, and SimulaWorks is a standalone product. The rest of SOLIDWORKS simulation portfolio is 100% integrated in SOLIDWORKS. So in this webinar, we are going to discuss mainly motion simulation, and motion simulation mainly is simulating the kinematic of the mechanism. So if you are having a mechanism and you want to get the kinematic analysis for it, like velocity, acceleration, or even the power consumed to actuate that mechanism, so motion simulation is your solution. Also, we are going to discuss the stress simulation in this webinar. And stress simulation mainly is for the stress analysis of your mechanism. Before we start this webinar, I'm going to ask you about something that have you tried to design a mechanism or a moving component before?
So, gentlemen, we are expecting a contribution from your side. Please, if you couldn't pick the answer, there is a small trick just to minimize the window. Just restore them, make it smaller, and then you will be able to answer correctly. Okay, great. A lot of contributions are there. Great. So let's close the poll and share the answer for you, Mahmoud. So I can see most of the audience today, yes, they are trying some of the mechanism studies in SOLIDWORKS, maybe simulation or in any other solution. So that's great.
That's great. Yeah. So in this webinar, if you are looking how to solve your mechanism and how to test this mechanism will withstand the boundary condition or not, this webinar is your solution. We are going to discuss about a case study, a challenge with DAP pipes. That challenge in DAP pipes, they wanted to design a pipe holder to hold and lift the pipe with various diameters and move it from a place to another place. That challenge with the holder mechanism and the power required to maintain the pipe held tightly. Also, the mechanism should hold multiple diameters of the pipes. So in that pipe, we need to insert some kind of mechanism, and that kind of mechanism will hold the pipe, and we can lift it from a place to another. So the problem that the physical testing will consume more time, because as you can see in the picture, the mechanism is big. So if you want to do a prototype, it will consume a lot of time and it will consume a lot of money. Also, if you would like to produce the version 2 of your design, it will make a lot of time as well. One of things in our challenge is to reduce the prevented maintenance. So with SolidWorks, we started to do a draft design, and they wanted to test that draft design with SolidWorks. So SolidWorks simulation participated to design and hold design that holder and tested it with SolidWorks simulation products. The question now, have you used SolidWorks motion simulation before or not?
So again, gentlemen, a lot of questions today. Very important question for us actually to understand who's in the audience today is using SolidWorks motion simulation. Okay, great.
Wow.
Even more contributors today. Okay, let's close the poll. Let's share the answer.
So it's
So it's 50-50 almost, Mahmoud.
Yeah. So today we are going to improve how you can use SolidWorks motion simulation in your daily design. So as a design for that challenge, there was some theoretical assumption. As we all know, the beginning of any design is a problem. We are facing a problem. Then this problem, we try to get a solution for it. Then we figure an idea to solve this solution. And that idea should based on some theoretical assumption. First assumption here is the state of equilibrium, which means how many points should I apply a reaction force to put the pipe in a state of equilibrium. Statically, we can use two arms or two forces or two reacting forces to hold that pipe, but this case is partially stable because the object still can flip. We can add a third arm or a third reaction force, and in that case, it will be safe. A fourth arm means force reaction force, and it will give more stability. But we are going to discuss how to optimize your design. So we need to get the best or the more appropriate design for it, which will be the three arms. Three arms will be the best choice to hold that pipe. So we now mostly know about the geometry. We need to discuss more about the material. We need to make assumption for the material properties, some elastic properties we need to know, the friction coefficient, of course, for the motion analysis, and some elastic properties and some yield about data about the yield strength. Also, we need to make sure that we are going to use a linear elastic material to avoid any non-linearity behavior in our study. So that's the theoretical assumption for the design. So when SolidWorks will participate? SolidWorks will participate as a simulation product or simulation solution in the next steps in the analysis scenario. We make two steps for our scenario. First step is kinematically solve the mechanism to get the kinematic parameters like distance, velocity, power, and even acceleration, and etc. After we get the output results, we can make some stress analysis to the mechanism to check if it will withstand the boundary condition or not. So for people who doesn't know what is SolidWorks, so SolidWorks is add-in in SolidWorks, and it's the SolidWorks Motion is an add-in in SolidWorks, and it's discussing how different parts within an assembly will not only depend on shape and joints condition, but also will depend on the physical factor such as mass properties, or each part can have an external applied force or motion. In SolidWorks Motion, it will allow the user to specify some factors, or these factors, calculate the resulting motion and show it in animation. The software will also allow you to measure the force or positions of the mechanism at different points in SolidWorks simulation. So that's SolidWorks simulation. How we can achieve a proper project in SolidWorks simulation, and that's first by doing the setup. The setup for the case study is by defining the whole boundary condition for my case study. So there is a gravity, for example, there is some kind of motors. We have to define the connection between each component with the base and the fixed ground, and etc. Next thing is to understand, or to fully understand, the timeline of the motion simulation. So as we can see, the timeline have so many keys. We have two kind of keys, black key and the yellow key. The black key is for the whole study. The blue key is for each parameter in the motion analysis. So the components, the connections, the motors, everything in the motion analysis is represented in the timeline with the blue key. So when you try to control that parameter, you only have to control that blue key. Next thing we need to know that we can apply or define the motors or actuators, springs, dampers, even external force or torque, and a gravity. So that's the interface briefly of SolidWorks motion simulation. Now we are going to discuss how SolidWorks simulation helped with this design. So the beginning of my study is to do the proper setup. The purpose of this motion simulation is to study the motion of the three arms on this mechanism and how they behave when they are inserted into the cavity of the pipe to hold it and lift it up. So after the initial modeling of this design using the engineering consideration, which we previously mentioned, we will start doing a visual diagnosis in SolidWorks motion. Now we are going to activate the motion analysis from the motion tab, and before that we have to activate the motion add-in from SolidWorks add-ins. And let's start doing our boundary condition. So the first boundary condition we are going to make is the gravity. So we are going to press gravity and select the Y direction for the gravity direction and press OK. Notice that the timeline has new keys. I will drag the black key from second number 5 to second number 20 to get more time for analysis. Now press calculate to visual diagnose the behavior and check what is required for this study. Notice what happened. The fixed ground still exists, but the whole mechanism had fallen. That's because I didn't define any contact between the fixed ground and the pipe. So let's do the contact, select the pipe. Yeah. And select the fixed ground. In this contact, there is no need to check the material box. Also, the static friction is not required. I only need to type the friction coefficient as 0.3 and some elastic properties data to define the contact more precisely. Now press OK and press calculate. Notice now the pipe is stable on the fixed ground, but the mechanism has fallen. That means I am moving in the right direction. So I need to make some contacts between the mechanism and the pipe to avoid falling it down. So I will continue to add the boundary condition. Now press contact. Okay, now I'm going to define the contact between the 3 arms and the pipe. So select the use contact group option, then select the concrete pipe on the other selection box. Continuing with the rest of the contact parameters, the elastic assumption are supposed to be known, but by our side, because we made that theoretical assumption in the beginning. After we done typing the elastic assumption, press OK, and then press calculate to update the results again. Then let's play it from the beginning with a slower rate to do our visual diagnosis. To check the performance, let's slower. With visual diagnosis, you will find the arms are sliding down while contacting the concrete. That's exactly what I want. You can check the difference between each condition by suppressing the recent contact and check the behavior, and you will see that the arms are sliding, penetrating the concrete pipe. I will unsuppress it, the contact, and operate it again. Adding more contacts, and this time between the 3 arms and the lifter, as the loads are transmitted mainly through these contacts. Make sure that you are typing the proper elastic properties and press calculate again to make the diagnosis. Calculate. Okay, now we have done this step. As you can see, it's sliding from the concrete wall, and that's exactly what I want. So next step, I will define the motors. First motor needed is the lifting motor, the motor which will lift the lifter up. So I will define it as a linear and define the phase, the direction. Now I need to define the bearing phase, and these phases are where the loads will be transmitted. Then we need to define the motion type, which will be expression. As I am having an equation for this kind of motion to lower the lifter and raise it and then lower it back, copy the expression from the outsource and paste it back. Now press OK. And again, go and add a new motor. The new motor is for the 3 arms. If you notice, the 3 arms are attached with links. These links are supposed to control the mounting and the unmounting mechanism. That's why I will define another motor to express the unmounting mechanism. So again, it's a linear motor, and press expression to copy and paste our equation. Now press OK. After we have finished, press calculate to check the output result. Notice that strange behavior. That strange behavior, it's like one arm still attached to the lifter and the other 2 arms are disconnected from the lifter. Also, they are moving randomly. Moreover, the connecting links have fallen. So I need to do more diagnose. Yeah. So as you can see, they left the connecting parts, they left each other and gone penetrating the lifter. And that behavior is not acceptable by my site. So we need to add some kind of new connection. So luckily I'm having a pulse. I will show them and I will define a new connection or a new contact between these bolts and the upper parts of the links. So I will select the 3 bolts from each set and select the links. We don't need friction, we just need some elastic properties. And after we have done here, let's press calculate. Check the output result. Okay, that's exactly what I want. It's smoothly sliding down, then in one point, dragging the pipe up, zoom out for more better view. Then, as you can see, the unmounting motor is disengaging the arms from the pipe, and that's exactly what I want. So I have reached my my kinematic condition from many testing. I made a contact, I defined a contact, then I made a test, then I defined another contact and I made another test. And step by step, I could be able to get the final result, as you can see. So more slower motion, you can see. Now I know if the arms are tall enough or not, if it need a rubber end or not. Also, I know if the initial assumption of the disengage distance is correct or not, because SOLIDWORKS motion simulation already calculated it for myself. So after I have done the kinematic setup and I'm sure that behavior is exactly what I want in the real life, so I will go to observe the results. After we have done our motion study setup, now we have come to as a final conclusion. The final conclusion from using SOLIDWORKS motion, that there is an ease of using SOLIDWORKS motion in the interface and in the timeline. Also, there are so many boundary conditions that I can define on my study, like gravity, like force, like whatever I want. The most important thing is to visual diagnose each step of my process to make sure that I am in the right path. So now, after we have done the motion setup for my design, I will go do the next step.
Sorry, Mahmoud, I think you didn't hear my question.
To calculate or to get the kinematic result needed from that study. Press result button and select a category, make it displacement, and the subcategory will be linear displacement, for example. And we are going to measure the distance between two objects or two entities to check the variation of the distance between these two entities versus time. Okay, and next we can calculate the acting force of the motor. Select force, select motor force, and for the object we are going to measure from the design tree, select lower lifter or the lifting motor. Now you can see the force in Newton, how it acts versus time. So it's going to increase while lifting, and then it will be like suddenly increase due to the shock in the motion. Then it will go down again with lowering the pipe. So now I can calculate the motor of the force. If I would like to find the consumed power of the motor, I can check for the consumed time. The best thing about motion simulation is you can find the highest power or the highest amplitude, and you can only find the amplitude of something versus time. Now we are going to calculate the distance of the second motor, which is necessary to disengage or to fully disengage the mechanism from the pipe. So the motor will start to act right now. So the maximum displacement required is 250. So if you are having any problem with your assumption, now you can correct them. You can get every and each parameter from your design or from your mechanism with this SOLIDWORKS motion simulation. So after we get the final result, we can find the conclusion. And the conclusion is to easily figure the kinematic properties of any mechanism, like displacement, like velocity, and you can adjust your assumption and change in your design to meet your requirement. Second thing is for easily calculating the power and the force for the motor, and that's for proper criteria selection of the motor. So if you want to have a mechanism and you don't know the power for your, how many horsepower required for this mechanism to work, the answer is SOLIDWORKS motion simulation. After we have finished kinematically solving our design, we need to know that after we made that design
Can I
and
interrupt you
make
for a
it
second,
work,
Mahmoud?
if that design will meet the boundary condition, the stress boundary condition, so I need to make a stress analysis for this mechanism, and that's the next step. So now we will take the boundary condition from the model reviewed and directly export it to SOLIDWORKS simulation study. First thing to confirm is making sure the bearing faces are selected in the mate feature. Like I said, the bearing face is where the force is transmitted. We need to make sure that the bearing phase are still defined in each arm connecting with the lifter. So go to simulation menu now and select import motion loads. Select the lifter as a component for the analysis and select the whole 54 frames for the calculation. Thus, the simulation study will calculate the stress for the whole 20 seconds of the motion. Open the lifter, and you will notice that there is a static study automatically created along with design study with 45 scenario. Click Run to check the 45 result in one click. After I have finished the calculation, I can get some data from this study, such as the history graph between the stress versus frame, to check where did the maximum stress happen. Now I can highlight the maximum stress, and the corresponding frame will be, which will be the 17th frame. Now I'm calculating the static study, which were previously defined by exporting the data from motion simulation. So now I can review the stress plot to know the minimum and the maximum place. I can edit the units. Also, I can change the deformation scale to be true scale to see the actual deformation. Also, I'm having the displacement plot and the strain. Now I'm adding the factor of safety plot to know where is the weak places. But this study is not my concern. The most concern is in the maximum von Mises place, which happens in the 17th frame. So I need to export the data from the 17th frame from the main study. Yeah, export and select lifter and type 17th. So he will automatically create a new static study called frame 17, and the parameters are already calculated, or sorry, defined. Now I'm calculating it and checking the results. So now I know the maximum stress happens in the 17th frame, and now I'm studying the 17th frame statically. So I know where is the maximum stress, where is the stress concentration, and I know this design is safe because it's below the yield point. Also, I can animate the deformation if I would like to see some more data. So now I started the design from a problem, then an idea. After that, we worked at that idea and made some assumption for it so that the geometry, resulted. We took this geometry to test it kinematically in SOLIDWORKS motion simulation to check if the mechanism is working properly or not. Then we took the data we get from SOLIDWORKS motion simulation to SOLIDWORKS simulation to check if the final design will withstand the boundary condition or not. And we find it that the final design will withstand the boundary condition. So now, as of the final conclusion of SOLIDWORKS motion simulation or simulation as a portfolio, now we can see how we can run each the kinematic and the stress in the same interface. Now the lifters have the factor of safety plots by working, and the variation of the factor of safety while the arm is working. Along in the same time, the force motor changing with the animation. And that's exactly what I want in the last thing or in the last step. I need to know if the design is kinematically working properly and it's safe from the stress analysis point of view. So after we have finished, now we can get to the conclusion, the final benefit of SOLIDWORKS. So why I would use SOLIDWORKS motion simulation? Well, simulation helped to reduce the number of prototypes are built for the physical testing. As you see that we have tested everything from the kinematic point of view and the stress analysis point of view. The physical testing is very time consuming and costly. Also, to improve the product quality by performing several what-if scenarios on the computer. So I can make a lot of scenarios and testing it on the motion analysis and SOLIDWORKS motion simulation and stress simulation to see if this scenario will work or not. So by validating your design on the computer, you will be able to catch the potential problem before the parts are manufactured, thus saving time and money.